Hey guys, today we're going to talk about converting rectangular equations into polar equations and vice versa. So far on Friday, all we did was individual coordinates. So like x comma y is, let's write this. So coordinates x comma y in rectangular form would change into r comma theta when it's in polar. So rectangular, polar. And there was certain formulas that we talked about on Friday to do this. Today we're going to do an entire equation. So we already know what rectangular equations look like. Y equals mx plus b, x equals y plus 2 squared minus 7. But we haven't done polar equations yet, but I promise they're super easy. The definition of a polar equation, it's up here, is that it somehow has r and theta in the equation. Uses r and theta. So when you're converting, you're going to use those same conversion equations that we did before. X is equal to r cosine theta, and y is equal to r sine theta. So for our first three examples, or I think it might be four, they're giving it to us in rectangular form, the form that we're used to seeing, x and y. We want to change it to polar form. So for example, let's look at this very first one. It kind of starts off simple. I have the line x equals negative 3. So this is just a vertical line if you can picture this in your head. XY plane, you find your negative 3. It'd be a vertical line through the negative 3. But I want to be able to graph it on a polar coordinate system, so I want to be able to graph it on a circle. So we're going to use the fact that x is equal to r cosine theta, and we're going to replace it here. Okay, but usually polar equations, they will have r equals or theta equals. So that cosine theta, we want to move it over to the other side. Sorry, this was supposed to be negative. So I'm going to do that by dividing by cosine theta. So that leaves me with r equals negative 3 over cosine theta. Now, it's honestly, this is fine if you want to leave it like that. It's just not very easy to graph. So we're going to use the fact. So this is, I'm going to put a star right here. This is one of our reciprocal identities. We're going to use the fact that 1 over cosine is just equal to secant. So I know we don't have the 1, but we do have the cosine on the bottom in the denominator. So I can replace that with secant. So my actual answer, I'm going to write as r equals negative 3 secant theta. So we haven't started graphing yet, but I promise that when we do start graphing, it's a lot easier to see it in this form. Okay, so we're only going to do the odd ones today. Let's look at number 3. Now we have y equals x squared. So again, this is should be a very familiar formula to you guys. This is just the quadratic parent function. This is just a plain old parabola. But we're going to use the fact that y can be written as r sine theta. So let's do that. And x can be written as r cosine theta. Only on this side it needs to be squared. And now let's solve for r. We want this equation to be r equals. So right now on the left, I'm not going to do anything. But on the right side, let's distribute that exponent. So this will be r squared cosine squared. All right. I do want r to be by itself. And right now there's r's on both sides of the equation. So I'll tell you what, let's divide both sides by r. So that's going to cancel it out of the left side. So I'll just have sine theta. And on the right side, it's not going to be squared anymore. It's just going to be regular r. Okay, so now the r is only on the right side. So if I want to get it alone, let's divide by the cosine squared. So I'm going to switch sides here a little bit. Let's put the r on the left equals sine theta over cosine squared theta. So again, you have to remember your identities. So first thing I'm going to do is split this up. So this would be sine over cosine times 1 over cosine. So because this was squared, that means that there's 2 cosines there on the bottom, so I just split it up. This first one, sine over cosine, hopefully we remember this, that's just another way of writing tangent. And then 1 over cosine, that's another reciprocal identity, that is just secant. Okay, let's look at our next one. I have x squared plus y squared equals 16. So this is straight from the conics unit. This is a circle. Center at the origin has a radius of 4. But I want to turn it into a polar equation. So x, we know, is r cosine theta. And then that needs to be squared. Plus y is r sine theta. Also needs to be squared. Equals 16. So we want to isolate the r. So first let's distribute this square. It should go to both things that are in there. So r squared cosine squared plus r squared sine squared equals 16. Now, I notice that they both have r squared. So since they have that in common, let's factor that out. So r squared on the outside, and then I would have cosine squared plus sine squared. Okay, but that part should look super familiar. Cosine squared plus sine squared, that is a Pythagorean identity. This whole thing just equals 1. So if it equals 1, I don't need to write it anymore. It would just be r squared, I mean technically there's an invisible 1 there, but we don't need it, is equal to 16. So this very easily just turns into r equals 4. Okay, and then one more where we have a rectangular equation and we're turning it into polar. We have x plus 1 squared plus y squared equals 1. So again, this is another circle, but this time the center is at negative 1, 0, and it has a radius of 1. So before I start plugging in the r cosine theta and the r sine theta, I do want to expand it a little bit. What I mean is this right here, that's squared. That means binomial times binomial, so I'm going to stretch that out by using FOIL, first, outside, inside, last. And it turned into that polynomial. But I still have the rest of this equation here. So plus y squared equals 1. Okay, now that I have it this way, I don't want anything that's a constant on the left. So I mean this 1 right here, let's move that over. So now I have x squared plus 2x. This cancels out, so plus y squared is equal to 0. It also happens to cancel out from the right. Now I'm going to plug in those things that we know. So x is r cosine theta squared plus 2, again, r cosine theta, because we have an x, plus r sine theta for y, that one is squared, equals 0. So for those exponents, let's actually multiply those in. This one here didn't have an exponent, but we're going to take off those parentheses. And then r squared sine squared. Cool. So I know from the previous problem that if I can get cosine squared and sine squared together, those will cancel out. Like, well, it'll just equal 1. So let's put those together. I also noticed that they both have r squares in front. So we're going to factor that out and have cosine squared plus sine squared. Okay, but then I still need to do something with this term. So I'm going to move it over to the other side. Since it's positive right now, when you move it, it's going to turn negative. So negative 2r cosine theta. So just like before, this part that I'm highlighting, that just equals 1. So I don't really even need to write that. It would just be r squared equals negative 2r cosine theta. Let's get r by itself. Like right now there's r's on both sides. So if I divide by r, on this side it'll cancel, but I'm left with r equals negative 2 cosine theta. So that is the equation of the circle now. Okay, so that is going from rectangular, so what we're used to seeing, into polar, so how we would have to graph it if we had one of those circle graphs. But now I want to go the other direction. So if I give you a circle graph, if I give you the polar equation, how do we simplify it to a rectangular equation? So those still, the same rules still apply. So r cosine is x, y sine, or r sine is y. But then there's two more that they want us to remember. R squared is equal to x squared plus y squared, and tangent of theta is equal to y over x. So 3 examples for this one. So since we're converting to rectangular form, at the end, we want our equations to have x and y. So we're going to start with a simple one. R equals 7. So there's no x, there's no y. And I mean, I want it to turn into x or y. I think we have to use this one over here in orange. R squared is equal to x squared plus y squared. So the problem is, right now it's not squared, but that's an easy fix. If I square the left, I need to also square the right just to keep everything equal. So r squared is equal to 49. Okay, well, r squared, like we just said, is equal to x squared plus y squared, so I'm going to replace it. Okay, and that's it. So what was just r equals 7 is now x squared plus y squared equals 49, and that you should recognize as a circle. Okay, let's do the next one. Now I have r is equal to 3 secant theta. Well, we're going to use the fact that, well, no, if I put x squared plus y squared, that still doesn't help me too much. Okay, so let's do this. See these equations up here? R cosine theta, R sine theta. Right now, I just have R. So if I were to multiply it by either sine or cosine, that should help me out a little bit. But which one do I multiply it by? So I'm going to take a look at the right side of this equation. Secant. Is there a way to cancel that out? So do you remember what the reciprocal secant is? I'm going to write it here to the side. Secant is equal to 1 over cosine. So that actually tells me it's probably going to be better to multiply by cosine. And I'll show you why just now. So if I multiply the left by cosine, I also need to multiply the right by cosine, just to keep them even. Well, r cosine theta if you look at up here, that's equal to x. So I can replace the left side with just x. Cool. But secant cosine, since they are reciprocals of each other, they cancel each other out. This is just going to be 3. Because of this fact right here, think of this as 1 over cosine times cosines. Cancels out, just a 1. So this is just a vertical line at 3. Okay, let's do one more. So what if we're given the equation r equals 2 sine theta? So again, I'm trying to get some x's and y's here. I can try that same trick. If I multiply by cosine on both sides, that's not going to cancel this out. If I multiply by sine on both sides, it's still not going to cancel that out. So what about if we square both sides? I think that should help. So r squared equals 2 sine theta squared. You know what? Scratch that. I don't even want to do that. So as you can see, I'm kind of doing this as I go along. What if instead of squaring, what if I multiply by r? So times r, and then sending over here, times r. So it's still going to be r squared, but on this side, I'll have 2, I'm going to put the r right here, 2r sine theta. So I think this is actually going to help me out more because r squared from above, I know I can replace that with x squared plus y squared. And then here, r sine theta, so just this part, let me highlight it actually, I think that'll be better. R sine theta, that's just another way of writing y. So this will be 2y. Okay, so this doesn't look familiar to me yet, so I think I want to move that 2y over to the other side. So we're going to subtract it. So now I have x squared plus y squared minus 2y equals 0. So that x squared is fine just the way it is. But here for the y's, we need to complete the square. So we need to add 1. By the way, completing the square, we did it a lot last unit, so I'm not going to explain it too much. If I add 1 there, I need to add 1 to both sides. So that'll make it to where I can factor this as y minus 1 squared. And then equals 1. Yeah, that makes sense. So this is a circle at the center, 0, 1, and has a radius of 1. Okay, guys, and that is converting polar equations into rectangular equations. So honestly, it all comes down to these 4 little equations here. The same ones that we used when we were converting our coordinates. It gets a little bit tricky when you're doing polar to rectangular because you have to remember some of your trig identities, but other than that, just follow the formulas and you should be good. And just let me know if you have any questions over anything.